Okay, so here we try to talk about how to really solve the constant coefficient linear ODE. So, so the first step is solve the homogeneous equation. So first, we try to consider a special case of second order, but if it is arbitrary order, it is still fine. But the case is that you should have learned how to solve quadratic equation, which means that solving a second order constant coefficient linear ODE will also need to solve a quadratic equation. If it is like a fifth order constant coefficient linear ODE, then you need to solve a fifth order polynomial equation. So that may not be solvable by hand. So here we just point out, okay, second order as a special case, okay. First order is too simple, okay, so second order will be general enough for you to understand how to solve the homogeneous equation. But if it's a high order, even third order, fourth order, maybe if the number is given good enough, then it will still be hand calculable. Okay, anyway, so if it is down to a second order constant coefficient ODE, it can be like a times the second derivative plus b times the first derivative plus c times the original function. So here, okay, and then of course we try to solve for the right hand side to be 0 for the homogeneous equation, so as the homogeneous solution. So so here we try to guess what is the solution. Okay, so don't ask why. Okay, here I directly tell you, okay, this should be the answer. This should be the answer. So we make it like exponential to s of t, s times t. Okay, exponential to s times t. Okay, maybe you ask why you make this guess. A straightforward answer is that it works. Okay, if you assume other form of the solution, it won't work. And then you may ask why. Can you have some simple idea, not necessarily rigorous reason? Is that if you try to take the derivative of exponential function, it turns out to be itself. Okay, so it is easy. So it is possible to cancel this kind of function. And then if you only have exponential to t, then you only turns out to be a plus b plus c to be 0. Then it won't help. The a plus b plus c doesn't necessarily to be add up to be 0. So here we try to put something in the front, exponential to s of t, so that when you take derivative, according to the chain rule, this s will come out as the order. So which means that if you take the second derivative, not only you have the exponent, the original function, you have the s squared due to the chain rule, okay? And then for the original function, of course, it is itself, and then for the first derivative, it should have this original function as well as one of the s, according to the chain rule, okay? So these two are due to the chain rule. Okay. So in that case, exponential to st are not 0 at any case, so we can just cancel them. And then it turns out to be as squared plus bs plus c equals 0. And then it is called auxiliary equation, okay, for the textbook I reference on. Or some of the other one, it may call it characteristic equations, okay, so different books, different people will call it with a different name, so maybe you just keep them in mind. So, and I think in some of the linear algebra textbook, it tends to use characteristic equation, okay, for solving the eigenvalue problem. Okay. So anyway, okay, first we try to solve this kind of second order homogeneous equation, and then it turns out to be like this, of course with this assumption. Okay, so this one we should be able to solve, because even for high school students, we know how to solve it. Okay, so here, I summarize the main point. Okay, we have this second order homogeneous equation, we have this assumption, and then we would like to solve this quadratic equation so that it will fulfill, okay, if we are able to find S, okay, it will be able to fulfill. So which means, okay, so in high school mathematics, you already know that, okay. Actually, okay, so maybe I don't try to use this minus sign, okay, so that you don't mix up. Okay, for the first case and the second case, it will be more easy. So, so for the first case, b squared minus 4ac is larger than 0. So you already know it has two distinct real roots, okay, two distinct real roots. So let's call the distinct real roots to be S1 and S2. They are different from each other because b squared minus 4ac is larger than 0, okay. S1 is not equal to S2. So in that case, the homogeneous equation will be like xc of t to be c1 times exponential to s1t and then plus c2 exponential to s2t. Okay, so yeah, so actually, of course, you need to slightly memorize it. But maybe you ask, okay, why is like that? Because by solving this one, if you get S to be S1 to be a solution, S equals S2 to be another solution, which means that, of course, this function is a solution to this homogeneous equation. And then this plugging in, okay, so which means that x1 equals, x1t equals exponential to s1t, x2t equals exponential to s2t are two functions that satisfy the original homogeneous equation. Okay, so as much as this one is linear, okay, it's linear, so which means that suppose on the left side we call it f, okay, the functional f, which means that f of x1t is equal to 0, and then f of x2t is also equal to 0. And then according to the linear property, just as what I mentioned, so which means that f of this stuff, okay, this is called the homogeneous equation, or sometimes it's called the complementary solution. Okay, so this f of c2t will be like a times, I should say c1 times this one, and then plus c2 times this one, which will be c1 times 0 plus c2 times 0, which will be 0. So which means that if x1t and x2t are homogeneous, are solution to the original homogeneous equation, which means that this general form is also the solution. So let's make it as general as possible. So this is the easiest case, okay? This is the easiest case. And then usually it won't appear. Usually it won't appear. And then for the second case, it is more complicated because it is like b squared minus 4ac is equal to 0, okay? Which means that it has repeat real roots, okay? S1 equals to S2. So if you just still follow the uppercase, it will be like, if you still follow, okay, S1 equals to S2, if you still write it as the xc of t equals to c1 x1, exponential to s1t plus c2 exponential to s2t. And s1 and s2 are actually the same. So it turns out to be c1 plus c2, c1 plus c2 exponential to s1t. Yeah, because s1 and s2 are equal to each other, they turns out to be a single function. Okay, so yeah, so you in this case you have missed something. Okay, you have missed something. So in that case, we need to find another solution. We need to find another solution because the s1 and s2 repeat, and in that case, these two functions are repeated also. So in that case, the answer is that xc of t will be c1 plus c2t, okay? We need to multiply by t. and then multiply by the original exponential to s1t. Okay, maybe you will ask why. Maybe you will ask why. The idea here is, I don't try to go through all the details. If you have interest to the math, you can try it yourself. You can make it like xc of t to be, let's say this is h of t multiplied by the exponential to s1t, and then you plug in back to here. You plug it back to here. Then you will finally find that, okay, you will be able to solve that h prime of t will be like a constant. Will be like a constant, let's say a, okay? So in that case, h prime of t will be like a linear function. Okay, and of course this general linear function also already include the original function. So this will be the homogeneous solution for the second case if b squared minus 4ac is equal to 0. So you need to slightly memorize this. Okay, it turns out to be like you multiply t to the original function as the second function. Okay, so this is a small trick there. Although this, for this case, it does not happen so frequently. The main part we want to tell is the most complicated case is the b squared minus 4ac to be less than 0. Okay, so even for a high school student, you know that for this case of b squared minus 4ac to be less than 0, it should be like complex conjugate roots. Okay, 共握的复数根. Okay, so which means that it should be like alpha plus or minus I beta. Okay, I will be the square root of -1. Okay, square root of -1, and I will need to say that I always like to write j to be square root of negative square root of -1. So later on when I write j, it means the square root of -1. Yeah, because for double E, for ECE, all the textbook will use J instead of I because A have been reserved for the currents. Okay, the current is more powerful. Okay, so we need to reserve I for the current. Okay, so we're leaving this imaginary number square root of -1 to be J, but it never minds. Okay, so actually, if we have the b squared minus 4ac to be less than 0, which means that we have complex conjugate root, which means that this alpha is the real part, and then we have two roots. One is plus the I beta, and then other one is minus the I beta. Okay, so this is not that difficult, but okay, the complicated part is here. So in that case, if we have the complex conjugate root like this, the complementary solution or the homogeneous solution will be like exponential to alpha t. So which means that you put the real part to here, and then you put the imaginary number, the imaginary part to here. C1 cosine beta t plus C2 sine of beta t. Okay, so this is hard to imagine. Okay, so why? Originally you just assume the solution to be exponential function, but why it comes out some trigonometry function? Okay, so let me tell you something. Something called the Euler's, okay, Euler's, let me see, Euler's formula. Okay, Euler's have many stuff. Okay, Euler's equation, Euler's identity, Euler's formula, something like that. Okay, for this one, I would like to mention is Euler's formula, which means that if we have exponential to j theta, okay, it will be cosine of theta plus j sine of theta. Okay, so this is called the Euler's formula. One special case is that the special case is called the Euler's identity. Euler's identity, okay, which is exponential to I pi plus 1 equals 0, okay? If you just plug in theta to be pi, okay, theta to be pi, which is 180 degree, okay? Theta to be pi, and then the left side will be like exponential to I pi or j pi, okay? And then the right side will be like cosine of 180 degree is -1. So moving to the left side will be plus 1, okay, to be like this. And then sine of pi will be 0. So turns out to be like that. Okay, which means theta to be pi, okay? And then ask why it is like that. Okay, for a not so rigorous proof is that you can use the Taylor series expansion or the Maclaurin series expansion, depending on how you call it. So which means that exponential to x is 1 plus x over 1 factorial plus x squared over 2 factorial plus ... up to infinity. Okay, so this is the Taylor series of the exponential function. And then for the cosine of theta will be, or cosine of x, cosine of theta is okay, so it will be 1 minus theta squared over 2 factorial plus theta to the 4th power over 4 factorial, and then minus theta to the 6th power over 6 factorial, and then up to the infinity, okay, plus minus for the even term, okay, and then sine of theta will be x minus theta cubed over 3 factorial plus theta fifth to the 5th power over 5 factorial, and then minus theta to the 7th power over 7 factorial. Okay, so I'm not sure whether you have learned it in the calculus class, but I hope so. So anyway, using this Taylor series expansion, if you try to plug in, okay, let's say this x to be j theta, then you will come up with a infinite series. And then you try to collect the terms, and then you can separate into, okay, cosine of theta and then j times sine of theta to be like that. Okay, so this is not a rigorous proof because this Taylor series expansion comes out from the real domain, okay, real value domain. But here we actually plug in some complex value into that function, so that we hope that it still converges. Okay, but anyway, this is not a rigorous proof, but it will be sufficient for engineering students, I suppose. Okay, so anyway, this is the Euler's formula. Okay, so why do I need to mention the Euler's formula? The reason is that here we have S1 to be alpha plus j beta, okay, and then S2 to be alpha minus j beta, okay. Of course, here is I, okay, but I always like to write j instead of I, okay, so forgive me for this part. Okay, and then here, okay, xc of t should be like something like, okay, let's say c1 exponential to s1t plus c2 exponential to s2t. Okay, so let's see what it is. And then c1 exponential to alpha plus j beta, and then plus c2 exponential to alpha minus j beta. So for exponential function, we can separate it as okay, we should have a t here, okay, s times t, okay, should be exponential to st, okay, for the xc of t, something like that. Okay, so we should have this t here. Okay, so first we should have alpha t and then exponential to j beta t, and then plus c2 exponential to alpha t exponential to negative j beta t. So it is straightforward as some algebraic computation. So here we have this common factor. Okay, so let me put it in the front. So exponential to alpha t, and then we have a c1 exponential to j beta t plus c2 exponential to minus j beta t. Okay, So here we need to make use of the Euler's formula. So exponential to alpha t will be the same, and then C1 here, exponential to j beta t will be like cosine of beta t plus j sine beta t. Okay, something like this. And then we also have plus C2 exponential, cosine of minus j beta t, because cosine is an even function, so it should be cosine of beta t, but sine is an odd function, so it turns out to be negative j sine beta t. Okay, like this. So we have a cosine here. Okay, so actually we have an exponential to alpha t. So we have a something called, let's say, a cosine of beta t, and then plus something times sine of beta t. Okay, you may ask, okay, we have an imaginary number here, but of course, this original function is a real function, so we expect that this stuff should be real value. Okay, so which means that C1 and C2 should be complex conjugate to each other, so that it will make both capital A and B are real value. So so here we have exponential to alpha t, and then something times cosine of beta t, and then plus something times sine of beta t, which is like this. Although that one is A, B, this one is C1, C2, but they are just unknown, undetermined variables. So no matter how you call it is fine. So this is the first step to solve the constant coefficient linear ODE, okay, for the three cases. And I will say, usually we will handle the last case, okay, as the most difficult one, okay. So yeah, for the first two cases, it is not interesting, okay. Usually, what we interest is the last case, because it is related to the trigonometry function, okay. Okay, so here are some examples of our first one. Okay, so 2x double prime minus 5x prime minus 3x equals 0. So the homogeneous equation is like changing the second derivative to s squared, first derivative to s, and then the original function to 1. Okay, so we have a 2s squared plus minus 5s minus 3 to be 0. So you can solve it as s1 to be negative 1/2 and then s2 to be 3. So the homogeneous solution will be C1 times exponential to S1t, this one negative t over 2, and then C2 times exponential to S2t, 3t. Okay, so this is easy. For the second one, x double prime minus 10x prime plus 25x equals 0. So you change double prime to be s squared, first prime to be s, and then x to be 1. Okay, so s squared minus 10s plus 25 to be 0, so you can easily find that S1 and S2 to be 5. So as it is a repeated variables, so the complementary solution or the homogeneous solution will be C1 plus C2t exponential to S1t, which is exponential to 5t, so like this. And then for the third case, x double prime plus 4x prime plus 7x to be 0. Okay, for this case, s squared plus 4s plus 7 to be 0. Okay, so just as what we did before. And then here, b squared minus 4ac is less than 0. This is complex conjugate roots. Okay, so this is negative b over 2, so to be negative 2. And then this part is square root of 4ac minus b squared over 2a, okay, over 2a, okay, so it will be negative, so it will be square root of 3, okay, so so one is negative 2 plus square root of 3i, and then the second one will be negative 2 plus square root of 3i. So in that case, the real part is negative 2. So we have an exponential to negative 2t, and then the imaginary part is square root of 3. So C1 cosine of square root of 3t, and then C2 sine of square root of 3t. So all of them are straightforward because we have already know how to solve it. You just need to plug in all these form of homogeneous solution. Okay, so this is just a numerical example. Okay, so here we come to the second step, okay, which looks like the most complicated case, okay, but what I want to show is this is the most general case, okay. Usually you will only see this one, maybe this one, and also maybe this one is probable, okay. Other are just like possible for mathematical, okay, but in the real world, I don't think it will occur, okay, if you don't try to make it too artificial. Okay, so I think actually for the first case, it's the easiest one, especially when it is like a constant. Okay, it's like a constant will be the most specific case. Okay, the specific case, the special case. And then sinusoidal function is also important. Exponential, not this one. Okay, should be this one. Exponential function times the sinusoidal function, because here we also have exponential function times the sinusoidal function, so that you expect that this one will be able to occur. Okay, so other than this function, you can other than this function, and this solution may not exist, or you may need to use Fourier transform or Laplace transform to do so. Because I will say actually know how to solve for the sinusoidal is sufficient, because Fourier transform or Laplace transform tells you that for arbitrary function, it can be decomposed into different frequency of sine, cosine. Okay, so in that case, knowing the solution for the sine, cosine should be enough. We don't need the tangent, because tangent is not a good function. It goes to infinity and infinite infinity. Yeah, so the first case is if the particular solution for the polynomial, so if g of t is the nth order polynomial, okay, we denote it as a p sub n. N is the order pn of t. Okay, we assume that xp of t to be also a nth order polynomial. So for example, if we have a constant coefficient linear ODE like this, on the left side is the second order, and then on the right side is first order polynomial. So in that case, the first step is still you need to find the homogeneous solution. Okay, don't try to skip it. Okay, don't try to skip it, because if you skip the homogeneous solution first, you may make some mistakes. For some of the case, you may make some mistakes. So you need to solve for the homogeneous function equation first by letting the right hand side 0. So for the first step, it will be like this, and then s squared minus 2s minus 3 equals 0. So you have a negative 1 plus 3 to be the 2 solution to the auxiliary equation. So this is the complementary solution, or we call it a homogeneous solution. Xc of t to be c1 exponential to negative t plus c2 exponential to 3t. And then here for the particular, so for the second step, the particular solution is that if we have a first order polynomial on the right side, we also assume that xp to be a first order polynomial of t, a plus bt. And then we plug in this one to the original differential equation, so that the second derivative will be 0, 0. This one will be b. This one is the original function. Okay, so actually you can just collect the terms. Okay, collect the terms like on the left side you should have minus 3bt and then plus this constant. Okay, so this is related to the first order t. Okay, and then on the right side, of course, it is a first order polynomial, so you have t here. So which means that if this equation holds, you should have the first order coefficient to be equal to each other, and then also the constant coefficient equal to each other. Okay, so which means that negative 3b equals to 4, and then this bracket equal to negative 5. So this is two unknown variables with two equations. Okay, so you'll be able to solve it. So actually a is this value, b is this value. So finally, you can plug in a and b back to here, so that this is the particular solution. And then for the first step, okay, the complete solution will be like the xc is here, which is this part, and then adding with the particular solution, okay, which is this one, by plugging a to be there, b to be there. So this is the particular solution. So this is xc of t, this is xp of t, like this. Okay, so for this case, not that difficult. And then for the second case, an exponential function. So if g of t is an exponential function, so which means g of t is something like exponential to alpha t, we can assume xp of t to be also an exponential function with the same exponent. So if g of t is like a polynomial times exponential function, then we also assume the particular solution to be like this. Okay, also like an f-order polynomial multiplied by the exponent. Okay, so this is a case. The same left side, and then on the right side 60, this is the first order polynomial, and then this one is the exponential function. So for the first step, this is the same as the previous one, so which means we have the same homogeneous solution. So for the second part, okay, xp, the particular solution will be like also this first order polynomial multiplied by this exponent. Okay, so it will be like the zero order multiplied by exponential to 2t, and then the first order part multiplied by the exponential 2t. We don't try to make it like a plus bt exponential 2t, yeah, because of course you consider they are the same, but it will be more easier for us to evaluate the second derivative because you need the product rule. Okay, so actually we need to plug in this xp back to this equation 2, so that you will have this second derivative minus the minus 2, and then the first derivative of xp, and then minus 3 of this particular solution, xp of t. Okay, so and still you also need to do some algebraic computation, so that turns out to be like on the left side will be like this times this part. Okay, so this one and this one will be the same, and then you also have these parts multiply exponential to 2t, and then of course originally you don't have exponential to 2t, which means that it should be a 0 multiplied by exponential to 2t. So that comparing the coefficient, you will have minus 3b equals 6, and then minus 3a plus 2b equals 0. And then also you have two unknown variables with two equations. So that you will be able to find a and b. And then finally, this is the complementary solution xt of t. This is the xp of t. So this is pretty straightforward. Okay, so and then the third case is for the particular solution of a sinusoidal function. G of t is a sinusoidal function. It can be either sine or cosine or both of them, okay? So no matter you only have a sine on the right side or only cosine on the right side or both sine and cosine on the right side, you still assume the particular solution to be a times cosine of beta t plus b times sine of beta t. Okay, no matter on the right side whether they have only one or two, you still assume all of them on the right side. So, and then for a more complicated case, if g of t is exponential function times sinusoidal function, it can be like this. It can be like this and or cosine. So in that case, we also assume that xp of t to be exponential. Okay, of course, this exponential function multiplied by this one, okay, which is here. And then for the third case, the most complicated case is if g of t is polynomial times the exponential times the sinusoidal. Of course, I don't think it will occur, but mathematically it is okay to solve. Of course, it is too horrible. It will be like polynomial times the exponential times the sinusoidal. So, of course, for the particular solution, you also assume it to be the polynomial with the same order, the exponential with the same exponent, and also the sinusoidal, both cosine and sine, with the same frequency. This is the most general case, okay, the most general case, although usually it won't occur. So here, let us see a particular solution. Let's see an example. So here on the left side, x double prime minus x prime plus x. On the right side, 2 sine of 3t. Okay, so for the first case, solve for the homogeneous equation. Okay, by letting the right hand side to be 0, so we have s squared minus s plus 1 equals 0. So clearly you can see that this equation has complex conjugate roots to be actually the real part is 1/2, and then the imaginary part is square root of 3 over 2 plus or minus for the two conjugate roots. Okay, so this is the complementary solution, nothing special. And then for the particular solution, this one is sine of 3t, So we should assume the particular solution to be a cosine of 3t plus b sine of 3t. And then we plug in this xp to the equation 3. So that we have xp double prime minus xp prime plus xp to be 2 sine of 3t. And then going through some calculation, you finally find out that, okay, this is cosine of 3t. Okay, so this part equals to 0, goes to here. And then sine of 3t here. So this bracket equals to 2, goes to here. Okay, and then finally, okay, two equations with two unknown, you can be able to solve a and b. And then finally, okay, this is the complementary solution or the homogeneous solution, xc of t, and then this is the particular solution. So you just follow the step, although the computation can be quite tedious, okay? But actually, you don't need to think of how I need to solve it, okay? You just need to follow this procedure and go to the end, then it will, if you don't make any mistakes in between, then you'll get the correct answer. Okay, so finally, before concluding these slides, okay, we have a we need to mention that there is a glitch for the method. Okay, so here we consider an example. Okay, here we have x double prime minus 5x prime plus 4x equals to this part. Okay, if you don't consider the homogeneous solution, just now I mentioned, okay, if you don't consider the homogeneous equation, sometimes you'll make mistakes. Here's the case. If you just ignore the homogeneous equation, so you may probably assume that xp to be a times exponential to t, and then you plug this one back to there, and then you find it won't work. The left side will always be 0, and then the right side will be 8 exponential to t, and then you won't be able to find a. Okay, so that won't work. The reason is that, okay, so first, of course, you need to solve for the homogeneous equation, like this. Okay, so for this case, the corresponding auxiliary equation or the characteristic equation is s squared minus 5s plus 4 equals 0. So which means that S1 is 1, S2 is 4, which means that for the complementary solution, you have this one and also this one as the xc of t. Okay, so you see, this is exponential to t, this is also exponential to t, but this one means that if you plug in exponential to t to the original left-hand side, it gives you a 0. So which means that this one won't be the particular solution. So here we need to make the xp of t to be this one multiplied by t. Just like the repeated root case, we need to multiply by t. We need to multiply by t. And then if you plug in this one back to the equation 4, then you will be able to find a. Okay, if you ask why do we need to multiply by t, you can also do the same thing. xp of t to be g of t times exponential to t, and then plug it back to the equation 4. Then you will be able to find that g of t will be like a linear function. Okay, so it gives you this t. Okay. So if unfortunately, if the right side have 8, let's say 2t exponential to t, okay, like this, then you need to assume the xp to be, then in that case you need to assume the xp of t to be a t squared exponential to t, okay, going one order even higher, okay. So that, so it is like the excitation, okay. So 被那个input 刺激，所以它就会激发到一个更高阶的状态。Okay, so excited by the input. Okay, so the linear system is excited by the input, so that it go up for an order. OK， 所以就是那种共振的状态，就是平常那种就是比如说一个玻璃杯，然后他一个人去对着那个玻璃杯大吼出那个玻璃杯的那个共振频率的话，也许那个玻璃杯会裂掉或者破掉这样，就是那个共振的现象。OK， so finally we have this to finalize to finish off this chapter this supplementary size, which is the initial value problem. So here we have a second order ODE with this stuff, okay, and then also with the initial value, So the first step is to solve for the homogeneous equation, and then it should be C1 cosine of t, C2 sine of t. And then for the xp of t, this is the first order polynomial. So we have the first order polynomial here, and then we have sine. But here we have already sine, so it makes it to be t cosine of t, t sine of t, like this. Oh, excited to the first order. And then we plug this xp back to the equation 5, So we will be able to find A, B, C, and D, and finally comes up with the complete solution to be C1 cosine of t plus C2 sine of t plus 4t minus 5t cosine of t. If you don't have this so-called initial condition, initial condition, then it is already done. But here we have the initial conditions, which means that we know x, when t equals 0, x is equal to 5. When t is equal to 0, x prime is equal to 1. Okay, so with these two initial conditions, we will be able to determine C1 and C2 uniquely by, very simple, you just plug in x to be 0 to this expression, then you will be able to find one equation. And then you also take the derivative, okay, take the derivative of this one, okay, take the derivative, you get this. And then you also plug in 0 to there, you also get another equation. So finally, you get two equations with two unknowns. So finally, you'll be able to find C1 and C2 uniquely. So finally, the complete solution with the initial condition will be like this, okay, for this second order ODE, second order constant coefficient ODE with these initial conditions. Okay.